All right, class. Good afternoon. Um, in case you missed the news or the meme review, um, the meme wars have been concluded and the students lost. So I have a big smile on my face because I defeated the students in the meme war. Um, so today's lesson is going to be pretty short. And are there going to be future meme wars? Will is asking. We could consider it. There was a request to have Mr. G host a meme review, and I emailed him, but he didn't reply. So maybe I'll try again. Yeah, but we should probably wait a little bit to let the memes build up again. So yeah, but yeah, I would be open to more meme wars. All right. So today we're talking about the relation or the relationship between electrical energy and other forms of energy. Okay. So let's suppose we have a circuit like this. Okay. And we want to know how much energy is going into the resistor. Well, I taught you guys an equation for power, and power is equal to current times voltage. Okay. Now so this is the power that's being output by the battery, and this is also the power that's being consumed by this resistor. Okay. So you might recall that power is energy per time. All right. So we could actually take this equation and solve it for the energy. So energy equals current times voltage times time. So what does this mean? It means that energy is deposited in the resistor, and the more time that the circuit is on for, the more energy is deposited. Okay. So now the question is, well, what does this resistor represent? Okay. So for example, what if this resistor represents something that is lifting another object? So maybe this is like a crane of some kind. In that case, you have electrical energy becomes, the crane is lifting something, right? So it's becoming gravitational potential energy. Okay. So if I wanted to set up an energy conservation equation, I would set electrical energy equal to gravitational potential energy. So what would that look like? It would be an equation that says IVT equals mgy. Okay. So this is an equation that basically tells you, as time goes on, the thing gets lifted higher and higher and higher up. So you could basically calculate how much time it's going to take to lift something using this type of an equation. All right. What if this resistor is representing a motor, for example? If it were a motor, you would have electrical energy, which I'll just call EE, becomes rotational kinetic energy. Okay, so the energy conservation equation that's relevant to this would be IVT. So that's the electrical energy deposited in the motor, becomes rotational kinetic energy, which is 1/2 I omega squared. We've got to be a little bit careful here because this I represents current and this I represents inertia. Okay. So if this were an electric motor, you have it turning into rotational kinetic energy. What if this resistor is representing a projectile launcher? There is an electrical powered projectile launcher. It's called a rail gun. You can check it out. They're pretty cool. In that case, you would have electrical energy becoming translational kinetic energy. Which means that IVT becomes 1/2 mv squared. All right. Trying to think if there's any others. Oh, you could even talk about a heater. Okay. So this resistor could represent just a space heater. In that case, you would have electrical energy is being transformed into thermal energy or heat. Okay. And in that case, you would have IVT equals the heat. You might recall from chemistry, and if you don't understand the thing that I'm putting on the right-hand side, do not worry about it at all. But I'm going to write it as C delta T, where C is called the heat capacity. And delta T is the change in temperature. Okay, so if you don't know this equation, don't worry about it. You should have learned it in chemistry. Oh, Theo, yeah, Theo came up with another one, which was electrical energy to elastic potential energy. So if you're using this to like stretch something, elastic, that would be IVT equals 1/2 kx squared. Sure. So you can have all these different conversions of energy. Going back to this really fast, delta T is in the room by a certain amount. Okay. Now, all of these equations are assuming that the energy conversion process is 100% efficient, which none of these are 100% efficient. So actually, in reality, you have the electrical energy is going to become the type of energy you want, and a portion of it is going to turn into heat. I'm denoting heat by Q. Okay. So all of these are not 100% efficient processes. You have the electrical energy, some of it goes into where you want it to go into, some of it becomes heat. Okay. So really that's my lesson, is I just wanted you to think about the conversion of electrical energy into other forms of energy. So you can see how it's kind of all related to the general theme of physics we've been studying throughout the school year. Today's daily item doesn't have to do with this. It has to do with the rest of the day off as far as my class is concerned. That's my lesson for today. I hope you guys have a great spring break, and I will talk to